Hi Math 3 students, Mrs. Robinson here to work Practice Benchmark Chapter 7 with you. Let's go ahead and get started. For questions 1 through 3, graph the function below. So we're going to graph some exponential functions. The basic of an exponential function, remember, if this value right here, the base, so you have y, the basic y equals, let's go, a times b to the x. B being your base, okay? So if your base is greater than 1, it's growth. Okay, our base cannot be 1 because 1 to any exponent, 1 squared is 1. 1 cubed is 1. 1 to the fourth is 1. So if it's 1, you just have a straight line. You don't have an exponential function. So your base cannot be 1. Your base can be between 0 and less than 1. That would give you decay, meaning it's a fraction, right? It's a fraction between 0 and 1. That gives you decay. But your base should also not be less than 0, because if your base is negative, when you square it, it's positive. But when you cube it, it's negative again. And when you take it to the fourth, it's positive. When you take it to the fifth power, any odd power, it's negative again. So you would jump up and down. It doesn't work. So if your base is greater than 1, you have growth. If it's between 0 and 1, you have decay. So you either have growth or decay, all right? Now we have a base that is greater than 1, so we have growth. Let's just do a little XY chart just to make sure we know what we're graphing here. All right, so if we start with 0, if I plug in 0, anything to the 0 power is 1. So unless you've got some shifting here, you should always have the 0.01, all right? If I plug in 1, 4 to the first power is 4. If I plug in 2 for x, 4 squared is 16, all right? So there's some points. Now I'm already off the graph, so let's go with some negative points. Let's do -1. If I do 4 to the negative first power, what is that? Remember what your negative exponents do. That's 1 over 4 to the first, or 1/4. Okay. If I do -2, that would be 4 to the -2 power, which is 1 over 4 squared, or 1 over 16. So we can see that this is going to get really small really fast. So let's plot. We're going to go over 0, up 1. And this is by 2's here, so we're going to go halfway right there. All right. That should be on all my exponential functions, unless I've done some shifting. I should have that 0.01, okay? And now I'm going to go, because anything to the 0 power is 1, right? So I'm going to go over 1, up 4. There's my next point. I'm going to go over 2, all the way up 16. Okay, and now let's do our negatives. So we went -1, which is right here, because, oh no, sorry, it's right here. -1 down a fourth, so just a little bit down, excuse me, up a fourth, just a little bit up. -2, a 16th. So if I go -3, it's going to start hugging this axis, right? So here's my line. I'm just going to sketch it here. And it's going to go up exponentially really fast. Sorry, it's so bumpy, right? And I have an asymptote at the x-axis, or y equals to 0. All right, there's my exponential y equals 4 to the x. Let's go on to the next one. Okay, this one, if I look at this, this is y equals something times b to the x. My base here is greater than 1, so I have an exponential. If my base was 1/3, I would have a decay, but I have an exponential, not a decay. So I start small and go big. Let's go ahead and do an XY chart for this one and see what I get. So if I plug in 0, now this is going to grow me or stretch me. Okay, this number here is going to stretch me. If I plug in 0 here, anything to the 0 power is 1. So this will be 1, but then I'm going to multiply it by 4. So instead of having the 0.01, I have the 0.04. Plug in 1, 3 to the first power is 3, but then you have to multiply it by 4, so you're going to get 12. So you can see it's going to go up quicker. So basically all the y values I would have had are going to be multiplied by 4. All right, plug in 2. 3 squared is 9, and 9 times 4, that's going to take us way off the graph, so we're going to be all the way at 36. All right, let's plug in some negatives. -1, 3 to the negative first power, that is going to be 1 over 3. And then we have to multiply that by 4, so that instead of getting 1/3, I get 4/3. Let's plug in -2. 3 to the -2 power, that's going to be 1 over 9, and I multiply that by 4, so that is going to be 4/9, and so on. So it's going to get closer to the graph a little bit slower because we multiply by 4. So let's go ahead and plot this. We're going to go over 0 up 4, so there's our point instead of 0, 1. We're going to go over 1 up 12, over 2 way up here at 36, way up here. Then -1, and then 4/3 is the same as 1 and 1/3. So we're going to go -1 up 1 1/3. -2 up 4/9. So that's about 4/9 is 4.5 over 9, about a half. So right about there. And then it's going to start hugging the graph slowly. So we're going to get something like this. And that's what it'll look like. Now, when you're working your practice benchmark, check it on Desmos and just make sure you've done it correctly. Hold up. Let's pull up Desmos. Okay, I pulled up Desmos, and my graph was y equals to 4 times 3 to the x power. All right, so here's my graph, and I'm going to clear this off. So that's not on there. Okay, there's my graph, and you can see I have the point 0, 4, which is exactly what I had, and then I had 1, and what else did I have? Oh, I cleared it off. So I plugged in 1, and I got 12. So 1, 12 is my next point. And this looks like a beautiful curve like what I drew. So I feel accurate. I feel like I did it correctly. So if I also, just so you know, if I did this y equals to 3 to the x power, just to see what it looks like when I don't multiply it by 4, you can see the blue was the original. I had the point 0, but the 4 stretched me up quicker. It stretched me up quicker. All right, so that's a stretch. Okay, remember the log is the inverse of the exponent. Okay, so remember on number 3, the log is the inverse of the exponent. Graphing logs isn't quite as simple as graphing the exponential function, but the inverse function would be y equals 3 to the x. The base is 3. So what I can do is graph this. Since the log is the inverse of the exponent, I could graph this and then just flip my x and y's. So if I were to plot the points for y equals 3 to the x, I would plug in 0, and I'm going to get out, anytime I plug in 0, I get out 1. If I plug in 1, 3 to the first is 3. If I plug in 2, 3 squared is 9. Do your negatives. Plug in -1, 3 to the -1, 3 to the -1 is 1/3. And then -2, 3 to the -2 is 1/9. So then just flip these. For the y equals log base 3 of x, I'm going to flip my x's and y's. That's going to look like this, since they're inverses of each other. I'm going to have 1/9 and -2. I'm going to have 1/3 for x and -1. I'm going to have 1, 0. So the logarithm, as long as you don't have any shifting or stretching, will always have the point 1, 0, opposite of this. Flip this. You'll have the point 3, 1 and the point 9, 2. So if I go ahead and graph this, I'm going to first plot the point 1, 0, not 0, 1, 1, 0 for the log. Then I'm going to go over 3, up 1, over 9, here's 9 all the way up the graph, up 2. And then I'm going to go over 1/3 just a little bit, down 1. Over 1/9 just a teeny tiny bit, down 2. So you can see it's going to start hugging the y-axis here. So my graph, if I could draw it nicely, and I knew I'd be wavy like that, sorry. It's hard to hold this still. My graph would look like this, whereas this, if I went ahead and drew, remember, inverses are reflections across the line y equals to x, the diagonal line here, okay? So if I were to graph this one in blue, okay, the exponential function, it should be the inverse of this. So basically I'm going to have 0, 1, over 1 up 3, over 2 up 9, way up here, and then my smaller points are going to be here. I'm basically going to have this in blue. So you can see they are reflections across this line. And then the asymptote for this one is the x-axis, or y equals to 0. But the asymptote for my log is going to be the y-axis, or x equals to 0 is the asymptote. Okay, and it has to be greater than, x has to be greater than 0 here. So go ahead and plot your points for the exponential of the log, and then flip the x and y to get your points. So there you have it. And let's go on to number 4. Okay, number 4 didn't ask us to graph. It just said identify the exponential function as, if it is increasing or decreasing. You need to then find any vertical and or horizontal asymptotes and x or y intercepts and the transformation from its parent function. So let's go ahead and look at the parent function. Y equals a to the a times b to the x. Okay, I know if this base is greater than 1, I have an exponential increasing. If it's between 0 and 1, I have a decreasing. So let's first look at our base. Our base is 1/3. So because it's between 0 and 1, I have a decreasing. So this will be decreasing. All right. And then I have a value here, an a value. So it's going to stretch. Okay, so my a equals to 8. It's going to stretch. Now, if that was negative, it would also reflect, but I don't have to worry about that. Vertical or horizontal asymptotes. Now, it's going to stretch, but because I am decreasing like this, my asymptote should still be this line, the x-axis. So I should have y equals to 0. The x-axis, remember x and y. The x-axis is the line y equals to 0 because y doesn't go up or down. It's on 0 and it stays there. So that will be my asymptote because I didn't shift. I didn't add 5 here. That would have shifted me up 5 and moved my asymptote, but I didn't. Okay, so my asymptote is still y equals to 0 for my asymptote. Okay. And that will be a horizontal. Okay, so there's my horizontal asymptote. X or y intercepts. Well, normally with this function I would have anytime I plug in 0, I get out 1. But I'm going to plug in 0 and get out 1. Then I'm going to multiply it by 8. So I'm going to have the y-intercept of 8. Now, if you're not sure, just check it. X and y-intercepts. To get your y-intercept, you plug in 0 for x. When I plug in 0, anything to the 0 power is 1, and 1 times 8 is 8. Okay. Now, what about, let's see, x-intercepts? I would plug in 0 for y. Well, I know it's not going to touch the x-axis because it's an asymptote here. So I just have a y-intercept of 8. I don't have to worry about the x-intercept. Unless I shifted it down, then I would have an x-intercept. Okay? And the transformation from its parent function, describe that. So from its parent function, it stretches by a factor of 8. Now you can go ahead and graph this. And let's look at what it looks like on Desmos. Let's bring it over here. So y equals to 8 times 1/3 to the x. So let's delete this. Delete. And then we're going to go 8 times, and then let's go 1/3 to the x power. And there we have it right there. And you can see, I've written, so what we said, it stretches by a factor of 8. It has a y-intercept of 8 right there. It has a asymptote at y equals to 0, which is the x-axis. Good. And it is decreasing. It starts high and it goes low. So we did a good job describing that. And let's leave. And that's how you do it. Okay, here's this guy. So let's go back to our original. Y equals a times b to the x. This is our base. Remember, if it's a fraction between 0 and 1, I decrease. So let's start with our base. So our base is equal to 1/4. So I decrease. Okay. Now, vertical or horizontal asymptotes. Now here's the deal. I can see this is going to shift me up 2. And I'm going to stretch by a factor of 5. So let's come back to that. Okay. What's the transformation from its parent function? I'm going to say, because my a value, a equals to 5, I stretch by a factor of 5. Okay. Now this right here is my k. Remember, x plus h, or excuse me, x minus h plus k. The x minus h part, the h shifts you left and right. The outside k part shifts you up and down. So if I write it for the exponential, it would look like this. B to the x minus h, that's why it's always the opposite direction, because it's minus h, opposite direction for left, right, plus k. The k is your up, down. The h is your left, right. Okay. This is my k, so I'm going to shift up 2. Up 2 shift. All right, so 1/4, it's a decreasing. It's stretched by a factor of 5, and it's an up 2 shift from its basic function. Okay. Now let's go ahead and talk about the x and y intercepts. Now, if I have a graph here, x and y intercepts, normally, if I plug in 0 to any function, I get out 1. I'm going to plug in 0, though. And I'm going to get out 1, and then I'm going to multiply it by 5. So I'm going to get 0, 5, but then I'm going to add 2. So I'm going to get out 7. Okay, so I plug in 0 and get out 7. So normally in a regular graph, if I just had this, I would have the point 0, 1, but I'd stretch it to 5. Okay, and I'd have a decreasing graph, something like this, and x and y. The x-axis, or y equals to 0, would be my asymptote, my horizontal asymptote. But I'm going to stretch, I'm going to go up by a factor of 2. So I'm going to move everything up 2, 1, 2. So now it's really going to be here. So instead of the x-axis, I'm going to have the line. Sorry, that was supposed to go beautifully. Oops. I'm going to have the line. Okay. Y equals to 2. This tells me my horizontal asymptote. If it's 0, it's y equals to 0. If I shift up 2, you're going to have an asymptote of y equals to 2. That will be your asymptote. Horizontal. Okay, so you shifted up 2. Instead of being at y equals to 0, you're at y equals to 2. And that looks like a z, sorry, it's a 2. Make it rounder. Okay, so we got our asymptotes. X or y intercepts. You're not going to touch the x-axis, you shifted up 2. But you're not going to be at 0, 5, you're going to be at 0, 7. That's how you get your y-intercept. So y-intercept at 7. And there it is, it's decreasing. You stretch by 5, you shift up 2. You have an asymptote at y equals to 2 and a y-intercept at 7, and I just kind of sketched it. And you can check it on Desmos.com and make sure you've done it right. All right, next one. Okay, so let's do number 6. And we gotta, I'm gonna pull it back so I can see all the things we gotta do. Okay, so number 6. We didn't have to graph these, it helps to graph. Now, remember, I'm gonna write this again. Y equals a times b to the x is our basic exponential. Shifting would be y equals a times b to the x minus h. Okay, so the h would shift us, since it's opposite, you would shift opposite direction, left or right. And then plus k, that's your up, down. Okay, so this is left, right. This is up, down. This is your stretch, shrink, or reflect. If it's negative, you reflect, okay? And you would reflect over the x-axis. So those are all your things. And then your base, of course, if your base is between 0 and 1, you decrease. And if your base is greater than 1, you increase. So those are your basics, all right? I'm going to erase this a bit so that we have more room to do this. Hold up. Come on, erase. Okay, so we have, just looking at this, I can already tell that we have a shifting, it's opposite. So if it's +2, I actually shift left 2. I shift up 1, I stretch by 7. I have a base that is greater than 1, so I increase. So I can answer a lot of this really quickly. So the transformation. So I'm going to say from the parent function, first I'm going to say b equals to 6. So I am increasing. Okay. A equals to 7. So I stretch by a factor of 7. And then h equals to 2. Since it's minus h, I do the opposite. Okay. So I'm going to go left 2, shift. Okay. K is equal to 1, so I go up 1, shift. And now I need my x and y intercepts and my asymptote. Remember your asymptote, since it was always at x equals to 0, or sorry, y equals to 0 or the x-axis, you're shifting up 1. So my horizontal asymptote is going to be y equals to 1. Okay, there's your horizontal asymptote. Now you want x or y intercepts. Well, let's just double check that. Okay, x, y intercepts. So if I want to plug in 0 for x to see what my y-intercept is, let's do that. If I plug in 0 for x, I get 0 plus 2. So this will be 6 squared. So I start off by going 6 squared, which is 36. Then I multiply 36 by 7. And then I add 1. So 253. So my y-intercept will be all the way up at 253. Okay, so you can see what this is going to do. Now remember, your basic increase goes like this. Okay, that is not what we have. What we have, that was just a sketch, and it always goes through 0, 1. What we have goes through 0, and it goes through 253. 0, 253, like way up here, I don't know. Okay, and then my horizontal asymptote shifted up 1, so instead of being at the x-axis, I shift up 1. This is where it shifts to. All right, it stretches by a factor of 7, so instead of going up like this, I'm going to go up really quickly. Okay, it shifted left 2, 1, 2, okay, and it shifted up 1. So from here, if I was just there, I stretched by a factor of 7. Okay, so I'm going to stretch up to 7, but I'm going to shift left 2 and up 1. So I'm just going to do something like this. Okay, and then it's going to come way down and hug this. All right, that's just an idea of what it would look like. You can check it on Desmos, and let's go ahead and check it on Desmos. Hold up. Okay, I left all of this so we can just double check and make sure that we've shifted correctly. So my original problem, I just put over it again. My base problem would be y equals 6 to the x. So there's my basic exponential where I would go through 0, 1. Now I stretch by a factor of 7, so it would go up to 0, 7, 5, 6, 7. But why do I have a y-intercept at 253? Why shouldn't it be at 0, 7? Well, that's because I shifted to the left 2 and up 1. So it would be right here. And then by the time I get all the way over to my y-axis, this line shifted left 2, and up 1, it's going to be way, 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 way up there. So let's go ahead and do that. Let's just do without, we're going to do this. Y equals to, just do the first part, 7 times 6 to the x power. Okay. And you can see it does have an intercept at 0, 7. But I then took my x and I shifted it left 2. So I'm going to add 2 because it's opposite. There it shifts it left 2. And then out here I'm going to shift it up 1. Okay. So when I do that, I shift it left 2 and up 1. When I actually hit the x-axis, I'm going to have to zoom way, way out. Where does it excuse me, the y-axis? I said x and I meant y. It's going to hit the y-axis way up here somewhere at 253. And it's hard to tell because it starts getting super close to it. It goes up so fast. Over here on this one. So way, way, way up here at 253. It looks like it's hugging the axis right now, but you get the idea. Okay, it just goes up really quickly, really, really fast. All right, so there is my actual graph. And that's what it would look like if it was zoomed in. I zoomed really in so we could see where the y-intercept was. But you can also see the horizontal asymptote shifts up to y equals to 1 right here. All right, guys. So that's how you double check it on Desmos. So let's go back and we've answered all the questions here for this one. We didn't actually have to graph. Okay, let's look at number 7. Number 7 asks us, hold on a second. Identify the logarithmic function if it's increasing or decreasing vertical or horizontal asymptotes and the transformation from the parent function. The parent function. So with this one, we just basically have the opposite of the exponential. And we need to know what the basic logarithm function looks like. If I have y equals to log base b of x, okay. And then I have an a value here, and I have, let's do this, same things. I have an x minus h plus k. This is going to shift me up and down. This shifts me left and right the opposite. This would stretch me. So looking at this, let's identify it. Well, this is going to give us a left shift by 1. Okay. This is going to be a down shift by 7. And then there's no stretching here. So I'm just going to have my basic log function. Now what's the base? No base is written. I don't have a b. When no base is written, your base is 10. That's your base. So you need to know what the basic logarithmic graph looks like. And remember, it is the inverse of the exponential. So the basic logarithmic graph looks like this, right? And if I wrote y equals base 10 to the x, and I did my xy chart for that, I'd plug in 0, get out 1. I plug in 1 and I get out 10. We'll switch these. Remember, if I switch these, that's my log graph. Okay, that is y equals 10 to the x. Y equals log, no base is written, it's base 10. Log base 10 of the x would be 1, 0, 10, 1. So I would be over here at 1, 0. You always have that point. And then you would have the point 10, 1. So I'm going to take my basic shift and I'm going to shift it left by 1. So instead of at 1, 0, I'm going to shift left 1. So I'm going to be at 0, 0. And then I'm going to shift down 7. So I'm going to go all the way down 7. So when I do that, now my graph is going to do something like this. Okay. Now, normally I have an asymptote, a vertical asymptote. This is the x-axis. My vertical asymptote is the y-axis, or basically x equals to 0. Because I shifted it left 1, that's going to shift my graph, my asymptote left 1. So x equals to -1 will now be my vertical asymptote. So that will be my vertical asymptote. Okay, so there's my vertical asymptote. It was at the y-axis, or x equals to 0. Now it's x equals to -1. I had to shift it over 1 for the red. Okay, so shift left by 1, shift down 7, and then you're going to have a vertical asymptote that shifts left 1. And that should work that one for you. Sorry, I didn't say if it's increasing or decreasing because it has a base of 10. So it's greater than 1, it's increasing, right? It's increasing. All right, on to number 8. Okay, on to number 8. An initial population of 820 quail increase at an annual rate of 23%. Write an exponential function to model the quail population. What will be the approximate population after 3 years? Okay, so we're given in a couple of the lessons, 7-2, I think. Let me just double check. Might be even 7-1. You're given the equation for exponential increase. And, hold on. Okay, I believe it is in 7-1. But basically your amount after time t is going to be your original amount, and then 1 plus r to the t power, okay? Where t will be the number of periods, and then r is your rate factor. And now r might be increasing or decreasing. It could be positive or negative. If it's decreasing, your rate would be negative and you would do 1 minus. If it's increasing, your rate would be positive. So this will be growth or decay depending on what you have. We have an increase here, so that will be growth, all right? And that will be your original amount, and then that will give you your new amount after t periods. So let's go ahead and use this formula. Our initial population, that's our original amount, okay? It increases at an annual rate of 23%. We put that in a decimal. That's our interest rate and its growth, okay? Write an exponential function to model this, and then we're going to figure out after 3 years. So our exponential function that will model this is just going to be, we're going to go the new amount, okay? After t periods, you're going to start with your initial amount, and then we're going to go 1 plus our rate. Our rate is 23%, in a decimal it's 0.23. So 1 plus 0.23 will be 1.23. And then we're going to do that to the number of periods. Okay, so there is a formula that we can use. Now we're going to approximate the population after 3 years. So we just plug in 3 there. Now just get out your calculator and just go 1.23 to the 3rd power. Then multiply it by 820. And that amount is going to be the population after 3 years. And I'm going to get approximately 1,526, rounding up a little bit. So make sure you know this formula, and you can use this formula for growth and decay. Okay, just double checked, and this formula is in 7-1. So make sure you know if R is growth, it is positive, right? And if it's decay, you do a subtraction here to get that rate, okay? What's the rate of increase or decrease? Basically, that's what it is. We have a rate of increase of 23%. So this will be growth. It would be decay if that was a rate of decrease. Make sure you know this formula, write it down, all right? So you're gonna need that, okay? Growth and decay formula. And then remember that rate of increase or decrease needs to be constant for this. Let's look at number 9. Number 9, the half-life of a certain radioactive material is 32 days. An initial amount of the material has a mass of 361 kilograms. The exponential function that models the decay of this is, I need to put a space there, sorry, is y equals 361, and then this growth or decay right here, since it's 1/2, it's less than 1, this is decay, right? And then we're going to take that to the 1 over 32 times x power. You have one problem like this on your homework in 7-2, and I told you y is equal to the mass times 1/2, and I put this in your notes next to this in the lesson, okay? Mass times 1/2, and then it's 1 over the half-life and that is times x, or t, for the amount of time. That's supposed to say half-life. You need this formula in to create this. So we can go like this. It has the initial amount with the mass. So remember, it's similar to this formula we just did for growth, right? Where you have A is your initial amount. 1 plus your rate, that would be growth. Or minus your rate would be decay. So if this is less than 1, you have decay. If it's more than 1, you have growth. Just like with your exponential functions, if this base is less than 1, it's decay. And then you take that to the time here. Now our time is half-life, okay? And that's why this is decay, it's half. And then the half-life is our time times the number of periods we do that. So if we model this, we're going to take our initial amount and we're going to go, here's our mass, 361, and it's a half-life. So we're going to go a decay of 1/2, and the half-life is 1 over, it decays in that amount of time in 32 days. So this will be 1 over 32. That is our actual time for a half-life. And now the T will be, they want to know how much radioactive material remains after 5 days. So we need to multiply this by 5. That will be our T, our time, 5 days, okay? So we're just going to plug this all in on a calculator. This can be a little tedious. I would go 1 over 32 times 5 first. Then I would go 0.5 and raise it to that power, and then multiply it by 361, okay? And if you do that, you get an approximation. And let's see, I went ahead and plugged this in on my calculator, and I got an approximation of, let's do this real quick. Okay. And that is in kilograms, okay? So 323.945 kilograms, rounding to the nearest thousandths, tenths, hundred thousandths, all right? And that's how you do that. So if you need the formula, I gave this to you on your homework for 9-2. It's in the lesson and videos. I'm sorry, 7-2, 7-2. It's in the lesson and videos. You need this for number like 23 or something. It's similar to this, all right? So really all you have to do here is plug in 5 for x to figure out how much remains. So half-life is how they figure out how old dinosaur bones are. When they figure out the carbon dating, and things decay and how much is left, they figure out how old it was. All right. Okay, I think this formula, suppose you invest $1,600 at an annual interest rate of 4.6 compounded continuously. How much will you have in the account after 4 years? So once again, from lesson 7-2, you're going to need this formula. A equals, or your new amount after time, a certain amount of time, is going to be your principal. And then E to the rate times the amount of time you have here. So all I need to do is know this formula and plug this in. And I'll put this in on the formula on the test just to remind you what the formula is. But make sure you study this formula and you know how to use it in 7-2. So we've got our new amount. We want to know how much will be in the account after 4 years. So our new amount is going to be our principal, which is 1,600 times E, and E is approximately 2.71. And then the rate in decimal, we need to move the decimal over 2 places, 0.046. And then our time in years will be 4. So I just literally plug this in on a calculator. I'm going to go 4 times 0.046, and then I'm going to go e to that power on my calculator, then multiply that by 1,600. So if you go ahead and do that on a calculator, you're going to get an approximation of 1923.22, and that's how much you'll have after 4 years at this interest rate compounded continuously. And that's what this E gives us, this continuous compounding. It's a beautiful formula. All right, so we start out with 1,600, we end up with 1,900. That's pretty good. All right, let's look at number 11. You opened a savings account and deposit 1,000. After a year of earning continuously compounding, or after earning continuously compounded interest, this is your balance. After 2 years, that's your balance. Assuming you make no deposits or withdrawal, find the equation for the best fitting exponential function to represent the balance of the account after X years. How much money will it be in your account after 10 years? So here's the problem with this. We're going to use that same formula, okay? So your new amount after T for time in years will be the principal times E to the rate, and then you're going to do that times time, the number of years. So they want to know after 10 years. But here's the problem with this problem. We have $1,000. That was our principal. We're going to plug that in, okay? And then we're going to go E to the rate, and then we want to know how much is there after 10 years. But here's the problem. We don't know the rate. What is our rate? Well, a couple ways you can look to find the rate. They give us some hints on the rate. They tell us the first year you deposit $1,000. After the first year you have this much, 1018.16. After the second year you have 1036. So you have 1036.66. Okay, compounding it continuously. So what I can do to figure out the rate is I'm just going to find the rate of increase from here to here. To get the rate of increase, I just subtract, I find the difference between the two. So I'm going to just subtract these two. Well, you can see when I subtract these two, I'm going to get 18.16 and then divide it by the original amount. So find the difference and divide by the original. Okay, when I do that, I'm going to get approximately, my rate's going to be 0.018. There's my rate. So if they don't give you the rate, go ahead and find the rate. Find the difference between the two and then divide it by the original amount. That's your rate of increase. The difference divided by the original amount. So go ahead and plug that in for the rate here. And you're just going to have 1,000 times E, and your rate is going to be 0.018. And then you multiply that by 10. So once again, on the calculator, multiply this out and then go E to this power. Then multiply that by 1,000. And after you do all that on a calculator, all right, if I do all that on the calculator, I should get approximately $1,197.22. All right, so that's how much I'll have after 10 years, compounding compounding continuously at a rate of 0.018, and if I move it over, it's a rate of 1.8%. That's why it doesn't move up too much. It's a very small interest rate. Okay, so make sure once again you know how to do this, and if they don't give you the rate, make sure you know how to find the rate by finding the difference between these two, and then go ahead and dividing by the original. You could have found the difference between these two and divided by its original, which would have been this one, and it would have given you the same rate. All right, so either will work. Okay. We're going to go ahead and start solving some logarithmic form equations and changing things around. Remember, I put properties of exponents and logarithms. I put it in Module 4, and I believe I put it again when you're going to take this test in Module 7. So I put this property of logs and exponents, print it out, and just use it as a reference, all right? So you've got your exponent properties here. B to the 0 is 1, b to the first, and so on and so forth. And if you look at these properties and how they apply, this is changing the base. X equals b to the y, and then you're going to keep the base the same and change the x and y. That's how I remember. Keep the base the same, change x and y to change back to a logarithm. Okay, and all of these properties go along. Log base b of 1 is always 0, because when I change it to the exponent, that's because b to the 0 is 1. And all of these properties about adding when you have a multiply, subtracting when you have a divide, when you have a power to a power, you bring it to the front, And then this property, if log base b of x equals log base b of y, that's true if and only if x equals y. So I can go ahead, if I have the same base, I know x equals y. And then the change of base formula. Another one that's not on here that I'd like you guys to keep is this one, and that is if b is a positive number, okay, other than 1, and then this works too. If b to the x equals b to the y, then that's true if and only if x equals to y. Okay, so I can use this and raise a power to a power. With that also, I can do this, where I raise both sides to a power because log base b of b is equal to x. So all of these are going to help me if I have all of this. So keep this with you. And let's go ahead and work some of these. Here we go. Okay, so number 12, write the equation in log form. And if I just keep this right here, maybe this will be helpful while we work through this. No, it's not staying. Okay, we want to write that equation in log form. So I remember when I change log to exponents, I keep my base and I change my x and y. Okay, so I keep my base and I change my x and y. So if I keep my base, I'm going to go log base of 2, and I change these two. So I'm going to go log base 2 of 32 equals 5. All right, and that's how I remember. Write the equation in exponential form. So once again, it's in log form. I keep my base and I change these two. So I'm going to go 4 to the negative 2 power equals 1 over 16. And I know that's true. 4 to the negative 2 power is 1 over 4 squared, which is 1 over 16. All right? We're going to write each expression as a single logarithm. So I'm going to use this property, and this property, and this property. So I know log base b of x to the y, I can bring the y in front, and it will be y times log base b of x. And I can also do the opposite. I can take this and put it up here. So if I want to do this as a single log, the first thing I need to do is move those numbers that are in front back to the exponents. So I'm going to write this as log base b of q cubed plus log base b of v to the 6th. Now I've got those out in front, I can use this property. If they're in the same base, then the addition, when I combine it to a single log, is multiplication. So this is going to be log base b of q cubed v to the 6th. So they're both the same base, and it's q cubed times v to the 6th. Multiply these out, and that's this property right here. All right, on to number 15. This is a subtraction. I'm going to use this rule. When it's a subtraction, in a single log, it's a division property. They have the same base, so I can go ahead and combine them as long as they have the same base. Log base 7 of it's going to be 50 divided by 5. The subtracted one is on bottom. Now that reduces. 50 goes into 5, and that's going to leave you log base 7 of 10. And that's how you do 15. All right, on to 16. Hold up. Okay, number 16, we're still combining these into a single log. So first, now we've got the natural log. Now remember, the natural log is equivalent to the log base e. Okay, that's what it is. It's log base e. And log, when it's not written, usually as a capital, is log base 10. These are both on our calculators. That's why they're useful. All right. We're going to take this up and put it here, and this up and put it here. So this is going to be the natural log of 3 cubed plus the natural log of c cubed. Now I use the same properties. Natural log is log base e. It's the same exact properties. It's an addition, so I'm going to combine them as a multiplication. This is going to equal log base 3 cubed c cubed. I can multiply, I said log and I meant natural log. 3 cubed c cubed, I can multiply them. Well, 3 cubed I know is 27. So this is the natural log of 27 c cubed. And I'm finished with that one. All right, a subtraction one, very similar to this. So I bring this in front, bring that in front, and it's going to be natural log of x cubed minus natural log of c squared. It's a subtraction, so I use my division property. This is going to be the natural log of x cubed divided by c squared. That is what it looks like, and you're finished. Okay, I just realized I didn't hit record for the last two problems, so I got to do them again. Here we go. Expand this. So we were taking these and putting it back. Now we're going to take this and expand it. This is multiplication, so use this property. We're going to go log base 3 of 11 plus, these are multiplied, log base 3 of p cubed. Now the cube you can bring in front. So bring that in front, and now you're finished. And I'm going to just erase it so I don't have to rewrite it. Done. All right, change of base formula is super useful because on my calculator I only have a, let's see, here it is over here. I only have a log 10, base 10, and the natural log base e. So I want to put it in one of those so I can use my calculator. Now the iPhone does have a little trick on it where it will let you do a log base 3 of 91. You have to play with it. If you take it, turn it to its side, you'll see it has log base 10, but then push second, and you'll see it has log base y, which means you could put base 3 of 91 in there. Okay, you have to play with the order that you put it in with a little bit first. But you can't use your iPhones on the test, so learn the change of base, okay? You can use a regular calculator. So the change of base just basically puts it in base B, which you will pick base 10 or base E. I always pick base 10, so I'll go like this. Log base 10, I'll write base 10 here, but you don't have to write base 10. When you don't write it, it means base 10. So log base 10 of 91. You pick this one first, and I remember this one goes below because it's already below, over log base 10 of 3. Plug this in on a calculator. Do log base 10 of 91, and then do log base 10 of 3, and then divide them. Okay, and you're going to get an approximate. Now my calculator will do that all in one foul swoop if I put parentheses around it so it knows. But if yours doesn't, you have to do it separately. That's okay. You'll get approximately 4.106. All right, on to the next one. We need to solve this, round to the nearest 10 thousandths. Now, for some reason it says that, and the answer key doesn't give it like that, so just make it close, and I will give you credit. All right, 4 to the 4x equals 8. Now to solve this, I got to get x out of the exponent. I don't know how to do that without logarithms. I'm going to use this property here. If log base b of x equals log base b of y, if and only if x equals y. It works backwards. If and only if means this works forwards and backwards. If this is true, I can do this. So if these two equal to each other, I can basically take the log of both sides. I'm going to do that so I can bring this out of the exponent and put it in the front like this. That gets that x out of the exponent, which is what I need. So I'm going to go log base 10, which I don't have to write, log base 10 of 4 to the 4x equals log base 10 of 8. Now this guy can come in front, and I get 4x log base 4 equals log, sorry I said base 4, log base 10 of 4 equals log base 10 of 8. Now I want to solve for x. This is all multiplied by x. So I'm going to divide by 4 log 4. Basically, I'm going to get rid of this and this all at once instead of doing it two different steps. Divide by 4 log 4. And I'm going to basically get x equals log base 10 of 8 over 4 log base 10 of 4. Now, I can plug this in on my calculator. I can go log 8 divided by parentheses 4 parentheses log 4, and then hit enter. Now if you can't do that all on a calculator like this and you have a basic scientific calculator, first type in log 4, multiply it by 4, get your answer, put that down here. Type in log 8, get that answer, then divide those two, and make sure you be as accurate as possible. Okay, so when you guys do that and you divide, you should get 0.375. Actually, you get like 3/8 if you did it. All right, so that is number 20. Let's look at 21. Okay, so 21, 15 to the 2x equals 36. Now I'd like to get that out, so I'm going to do the same thing. I'm going to log both sides, base 10. So log base 10 of 15 to the 2x is log base 10 of 36. Bring this in front, use that same method, and then I'll get 2x is log of 15. 2x times log of 15 equals log of 36. I'd like x to solve, so instead of dividing by log of 15 and 2, I'm just going to divide by them at the same time. So that eliminates these, and it just leaves me with x. Divide by log of 15. Oh, I forgot the 2. Shame. Put that there. Okay. So now I'm going to get log of, x equals log of 36 over 2 log of 15. And once again, type in log 15 times 2, write that here. Type in log 36, write that here. Divide them. So I'm going to do this in one fell swoop on my calculator. I'm going to do, let's see what I get. I get approximately 0.6616. There you have it. That's how you do 22. Okay, 23, to solve this one, let's just scroll it up a bit. To solve this one, I need to solve for x, but I've got two different logs here. And I can go 1 minus log 14, but then I'm dealing with logs on both sides. Let's first combine them into one log and see if that helps me. Let's go log, and it's base 10. To combine these back to one log, I'm going to use this property. They have the same base, so I can combine them into one log by multiplying them. So I multiply 5x times 14. Right? They have the same base, so I'm just going to go 5x times 14. That's one log, and that still equals 1. Well, 5x times 14, that's 70x. Log of 70x equals 1. All right, well, how am I going to solve this? I'd like to get the x out of here. So I can go ahead and get rid of the log if I use this property, the property that I said over here, to get this to happen. If b to the log base b of x will just equal x. Well, if I know b to the x equals b to the y, and it's not writing, b to the y, it doesn't, hold on. B to the x equals b to the, why doesn't it, okay, it won't write there. I don't know why. B to the x equals b to the y if and only if works x equals to y. So I can do this here. Sorry, that erased it. We had log of 70x is what we had, and that equals to 1. Okay, when I combine these, I got log 70x. So I'm just going to do this. This is log base 10. So I'm going to do b to this equals b to this. So I'm going to raise this up from a base of 10. I'm going to go, well, if x equals y, then b to the x equals b to the y. So let's go 10 to the this equals 10 to the this. Okay? So by doing so, I'm going to use this property. B to the log base b of x just as x. So this is 10 to the log, this is log base 10, it's just not written. 10 to the log base 10 of this is just going to be just x. So it's just going to be 70x. And that will equal 10 to the first, which is just 10. Now to solve for x, I just divide both sides by 70. Okay, and I'm going to get x equals 10 divided by 70. So I can do that as 1/7 or 0.14. Either will work. Okay, another way to do this, if you don't want to raise both sides, if you were at this point, log base 10 of 70x equals 1. And I wrote the base 10 here. Okay, you can use change of base here, or excuse me, you can use the exponent change, not the change of base. You can change from an exponent or a logarithm to an exponent, and you'll keep your base. and you switch these. This will be 10 to the first equals 70x. Another way to do it, probably a simpler way than what I did. And then divide both sides by 70 again, you get the same answer. X equals 1/7. So you can change this to an exponent and solve that way. All right, let's go ahead and do this one. 6 e to the 4x minus 2 equals 3. Okay, first thing you always want to do is to isolate the x, get rid of stuff you can get rid of quickly, like get rid of the 2 on both sides. Do that first. Okay, and then you're going to get 6e to the 4x equals 5. Now another thing you can get rid of easily is the 6. Divide both sides by 6. And that gives you e to the 4x equals 5/6. All right, now we would like to get x by itself. Now if I change this to log form, if I go log base e, so I keep the base, so that's going to be the natural log, keep the base, and switch these. Log base e of 5/6 will equal 4x. That will be perfect. I know log base e is the natural log. The natural log of 5/6 equals 4x. Now to solve for x, I just divide by 4. So x is going to be natural log of 5/6 over 4, and I do this on my calculator. So I go natural log of 5, in parentheses 5 divided by 6, or divide 5/6 and then do the natural log of that amount. Then divide it by 4. Okay, I'm going to get a negative number here. It's going to be negative 0.0, rounding to 0.046. 10 to 100, that's the thousandths place, not the 10,000ths place, but that works. Okay, so make sure you divide this and then go natural log of this and then divide by 4 on a calculator. Okay, I have a calculator that will put this in parentheses and do it all at once. But if you don't, divide it first and then do the natural log of that. So once again here, we isolated everything until we couldn't go anymore. Okay, the x is still here, so I got rid of everything that was surrounding that x. The x was still here. Now I changed this to a log form. Okay, when I change to a log form, the rule is you keep your base, so I keep my base and I put it as the base of the log, and then I change the x and the y, so I move this over to here and this over to here, and that's how I go from a log to an exponent. Okay, and then I finished by dividing both sides by 4, and now I did natural log of 5/6 divided by 4, and I got this. All right, last one. Okay, natural log of 2x minus 1 equals 8. So here's what I want to do for this one. I would like to get this out of the log. So a couple choices. I could use this and the thing I showed you before, the b to the x equals b to the y, if and only if x equals to y. So I could raise these both to the e power and pull this out using this. Or I can just change it to an exponent. Natural log is log base e. Here. Log base e of 2x minus 1. That's supposed to be minus. And that would be equal to 8. So I just wrote this as log base e. Now I'm going to do the whole thing and I'm going to change it to an exponent. So keep your base, e, then switch these. E to the 8th equals 2x minus 1. Great, now I can solve for x. I just add 1 to both sides, and I get e to the 8th plus 1 equals 2x. Now I just divide by 2 on both sides. Divide this whole thing by 2, and I ran out of room down here, so let's write it up here. And I'm going to get e to the 8th plus 1 divided by 2 equals x. Do this on a calculator. Go e to the 8th, add 1, divide by 2. Dun, dun, dun. You're going to get an approximation over here. Let's write it over here and this way. Those are my ugly squigglies. Approximately 1490.79. Just kidding. 0.979. And I erased that last one, but that was the final answer. So Let me know if you have any questions, guys. It was 1,490. I think that's what it was. But I think the recording got it. So just in case that last answer, and you should have, it was 1,490.979. All right. Okay, I think it erased that last bit. So here's your solution. Go ahead and that's the whole test, guys. Go ahead and email me if you have any questions. Make sure you print this out and let it help you and remind you of the properties, and have a good day. Oops. And have a good day.